Okay, so um, nucleophiles with anionic groups, they're not substrates. So flavin monooxygenase is more selective. It's more stereoselective. So for example, they both oxidize nicotine, both cytochrome P450 and flavin monooxygenase, but flavin monooxygenase only gives one isomer, whereas cytochrome P450 gives two. And so that gives you an idea that these enzymes are a little bit different. The active sites are a little bit different, and they're more selective. So here's some of the reactions of flavin monooxygenase. So this is good though, because you want to know what's going to happen to your drugs as they get metabolized and what's likely to happen to your drugs in the body, because that's going to give you a sense also of what to look for when you're doing your metabolism studies, when you're making your drugs and you want to prove that your drug is safe. Okay, so another thing that um, happens a lot, especially with cytochrome P450, is the formation of arene oxides, and this especially happens with electron-rich double bonds. So here in this case, we have the arene oxide that's isolated. So this is from, they found a reaction that was called the NIH shift, and we'll talk more about this, because basically what happens is that the NIH were the ones to figure out that cytochrome P450, scientists at the NIH were ones to figure out that cytochrome P450 did this, and then they found out that it also rearranges. So the mechanism is this, which is basically you have this radical type mechanism that's happening, and it's quite a complicated mechanism, but you're essentially forming an epoxide intermediate. And so this epoxide can do a lot of things. It can rearrange to form the phenol, right? So that gains aromaticity. It can be turned into the diol, by the epoxide hydrolase. It could be turned into a glutathione S transferase. Um, adduct, homework alert. So that would be an example of phase 2 metabolism as well. It can also react with other molecular, macromolecular nucleophiles. And some of this could be phase 2 metabolism, but it could also end up being toxic effects. If you remember how cigarette smoke causes cancer that we talked about before, this is due to the formation of an arene oxide. We'll talk more about that in a second. So one thing that the arene oxides do is that they can rearrange to phenols. Um, and so this was figured out doing some really elegant experiments where they can look and see that you get a shift of that you get a 1-2 shift of the proton next to the next to the epoxide bond. And they also have deprotonation. You don't have to worry too much about this as well, but it's just some really nice kinetic experiments. And basically, what these kinetic experiments do is that when you deuterate a site that you think is, say, going to be deprotonated, it's going to slow down the deprotonation. And so this will make another CH site favor. So this is always the case. This is known as a kinetic isotope effect, is that basically when you change the isotope for a molecule for a heavier isotope, you're going to slow down the kinetics of the reaction. And so if you think that a reaction's happening at a certain proton in your molecule, one of the things that you can do to prove that it's happening at that proton is substitute that proton for a deuterium, and that's going to slow down the rate of the reaction. And if your substituted molecule that has a deuterium substituted for the proton now has a slower rate, then you have proven that the reaction was taking place at that proton. So that's known as a kinetic isotope effect. So we use this a fair bit in metabolism studies when we can. And so basically, you can do that that rate of reaction. This holds true for metabolism studies, and so this is why you can, if you think your drug's being metabolized at a certain spot, preferentially in the drug, you'd put a deuterium there, and you'd see if the half-life was now extended, if the amount of time it stayed in circulation is extended. In this case, there was a number of sites of metabolism, and they were able to cut off some of those by inserting these deuteriums at easily synthetically accessible points, and they're able to extend the half-life in the blood because it's not being metabolized as quickly. So this is kind of a side note, is that the NIH shift can happen with substituents, not just H. It can happen with, say, chloro groups as well. The NIH shift, this also, there's not an enzyme. This can happen in your flask as well if you're an organic chemist running a reaction. NIH shifts with electron withdrawing groups doesn't tend to happen. So things like parachlorines or parafluorine are going to inactivate the ring, so you don't get the same NIH shift. The nitro will behave if there's a nitro substitution, and it can do it. It will participate in that NIH shift, though. So the reaction with cytochrome P450 is the reaction that the slides talk about. And so basically it's electrophilic aromatic substitution. So that means if it's got electron withdrawing groups, it's not going to happen. And for electrons with more than one aromatic rings, you can extend this from 2 to many more. The more electron rich one is usually hydroxylated. Okay. This is also species specific, and this is even, dogs and humans are pretty close, but dogs and humans start hydroxylating compounds in different places. So notice both of these, we don't know what the R groups are, so we can't tell how electron rich or how electron poor these are, but they're both arenes, and so those are what are getting metabolized in this case. And so what can happen is that this happens first, right? Is that you form this epoxide by action of cytochrome P450 on your arene, on your aryl system. So this was from cytochrome P450, and now what we're showing here is that epoxide hydrolase, another metabolism enzyme, can come in and it can turn the arene into a catechol, a diol. So it can turn it into a diol. This diol can be oxidized to quinones or other structures. Homework alert. So now you have cytochrome P450, an example of how it acts on an arene system to form, again, this is a phase 2 metabolite. So once you add in that glutathione, that's great. The reason that I would want to do this with glutathione S transferase is, remember, glutathione is a 3 amino acid, it's like a peptide, right? It's like a 3 amino acid peptide. And so if you have a peptide on this lipophilic system, you've made it a lot more water soluble. And that's great because that means it's likely to get excreted through the kidneys, and it can be way more soluble in water. And so whenever that happens, the likelihood that it'll be successfully secreted through the urine goes up. and it's not going to want to interact with cells. It's not going to want to interact with cell membranes. So from your body's point of view, it got that compound handled. So that's really a great reason to form an epoxide on an aryl system. So an example of this when this goes wrong is in the formation of the common combustion byproduct, which is benzo alpha pyrene. And so this is a combustion product that's formed in smoke. And what can happen, right, is that it forms some of these structures that are epoxides that can readily interact with DNA and RNA. So they can act as alkylators. So this is what is chiefly causing cancer. One of the chief causes of cancer due to smoking or lung cancer. And notice that this has been known about. They kind of had this soot and cancer noted in 1775. And that was chimney sweeps developing skin cancer, actually, from having this on their skin. Okay, so alkenes can also be epoxidized. So this is carbamazepine, and so carbamazepine, it's anti-seizure. This is a seizure medication, and so it gets oxidized. This can also, one of the nice things about carbamazepine is that its product is also, its oxidation product, the initial oxidation product is also an anticonvulsant, and it's not until it's worked upon by cytochrome epoxide hydrolase that it is no longer an anticonvulsant. Okay, here's another extremely toxic molecule, which is aflatoxin, and that again can cause cancer. So this is formed in different fungi. It's, for example, in improperly cured peanuts, and it can be oxidized. This should say cytochrome P450 can oxidize this electron rich. Notice this is a very electron rich double bond here, and it can form an adduct with DNA. Again, it reacts with those DNA bases, and then it can cause mutations because the base gets misread. Oxidation of carbons adjacent to aromatic sp2 centers. So that means you can start, for example, in amyltryptamine, this is a tricyclic antidepressant, you can start oxidizing here or here. This is again kind of I would say this is kind of you can start to oxidize either one of these protons depending on how it binds with cytochrome P450. Here we're able to do an allylic hydroxylation. So we're able to hydroxylate here. And you're also able to oxidize adjacent to a carbonyl, at least in this case. So this is really, you're able, again, this is that case of the proton being close or being somewhat acidic. There's also cases, again, so what I'm trying to say here is there's a lot of different reactions the cytochrome P450 can do and flavin monooxygenase can do. There's a lot of different reactions that these can do to start detoxifying a drug. So in this case, they can either omega from this anion. This is sodium valproate, so this is another it's given for people that have seizure disorders a lot of times. And in this case, both of these carbons are oxidized, but here you have an example of a vasodilator where it's only oxidized here. So it's only hydroxylated here. There's hydroxyls here and here, but it's only a hydroxyl here. So these, you would say, why wouldn't it put a hydroxyl here? Well, this is actually, there's low rotation. This is very structured molecule because it has all these cyclohexyl type groups, and so it's not always obvious, or it's frequently not obvious to us as chemists where it's going to be oxidized, but it can be oxidized in a number of places. It's a pretty impressive enzyme. Also notice you get beta elimination, and that hydroxyl, you can start oxidizing. This is what happens when you hydroxylate beta to carbonyl group. You can start to beta eliminate into that carbonyl, but through resonance. You can also get oxidative deamination. We saw before how some of that could work in oxidation. So we saw that with flavin monooxygenase and in oxidation. We are able to see the aryl amines are turned into nitro groups, and that goes through a nitroso species. And amides are turned into hydroxamic acids. So oxidative deamination is going to just be an elimination. We eliminate ammonia. So here's an example of this. Amphetamine is going to be oxidatively deaminated to the corresponding phenethyl ketone in ammonia. And so we can see that this is from oxygen too by feeding in O18. So this is isotopically labeled oxygen. Oxygen is normally O16 is the isotope. And so we're able to see that this isotope is showing up. So through flavin monooxygenase will also oxidize amphetamine, and you'll get the same product at the end of the day. So typically basic amines are going to be oxidized by flavin, like it says here. Non-basic, such as amides, those are going to be cytochrome P450. But if it's an aromatic amide, it could be both alpha protons or flavin. So this is a good bit of information here in red to kind of give you a picture of the different specificities between the enzyme. Okay, so here's an alternative pathway that you can get to a ketone through this oxidation. So it's kind of a mechanistic point, right? You can obviously turn that into a ketone there. So again, we have oxidative N-dealkylation, oxidative deamination, N-oxidation. And these are all for secondary amines and amides. So basically, what's going to happen is a lot of the amines and the amides, your body's ready to, your body is ready to break down these amides and these amines. So they do it through a number of steps. So basically, you can start to get these different eliminations. So you can do this by oxidizing the alpha proton as well. For example, here you can do this too for something like propranolol. You're able to oxidize. So that's a blood pressure lowering drug. You're able to oxidize in multiple places. Fenfluramine is oxidized that you can start to get the nitro compound. For tertiary amines and amides, the main upshot is that you're not able to get oxidative deamination. So that's for tertiary amines and amides. You're not able to get oxidative deamination. So you can see something that's really helpful is oxidative indealkylation. You can control it, and then we know a lot about it, and so that's very helpful. And so notice here the rates here in green. So the rate of metabolism is going to be different for how many methyl groups are on the mean amine. So this means that, or another example here, sorry, that kind of adds on to this. Let me try to, is there anything else I want to say here? Okay, so yeah, it slows down, the amount of methylation slow down. So the indealkylation tertiary amines, that's the fastest to get dealkylated. Secondary amines, second fastest. Primary amines, that is oxidative deamination. That's the slowest. So that's a little different reaction. And another example of this is that the indemethylation of one isomer is slower than the other. So that's something else to consider. So when they're demethylating here, it depends on these isomers, which one is going to be faster and which one is going to be slower. Here's another, this is another kind of interesting example. Well, it's pretty interesting, is that you have two enantiomers of this initial compound here. This is really interesting, right? Because the S enantiomer of this compound is a weak antidepressant. And then when it's broken down, it's turned into amphetamine and methamphetamine. The S form of amphetamine and methamphetamine. So those are the S enantiomer of methamphetamine is a stronger one. The S enantiomer of the amphetamine is the stronger stimulant, the one that has the drug effects. The R enantiomer of this, fortunately enough for us, is a potent monoamine oxidase inhibitor. So it's a potent antidepressant that prohibits the oxidation of dopamine and serotonin in your brain. It inhibits them from being turned over as effectively. And so that means there's more of them hanging around, so you feel better. And when it's oxidized into R-amphetamine and R-methamphetamine. So those are weaker. So you only want to use this enantiomer. So this is another example of why you need to know what your drug is being turned into in the body, because you might not have predicted that. So you have some other effects though with R-amphetamine, and so in the end of the day, this is the drug that works better. That's kind of the drug that's gonna be used. So it's like this is the one they'd start out initially with, and they're like, okay, we need to go to this aminoindane because there's a little less side effects when it's processed biologically. Okay. Acyclic tertiary amine oxidation. Okay, here's an example using nicotine. And in this case, it has a number of different pathways, how it can be broken down. What we're finding that there's an iminium ion that's the intermediate for all these. So basically you're going to form this kind of hydroxyl group, and then eventually the iminium. In this case, the formation of that 5-membered ring meant they could trap this metabolic intermediate for lidocaine. So this is a common anesthetic, topical anesthetic. So they're able to isolate this guy. Here's an example again of another inoxidation. In dogs, they only form one form of the inoxide, with the inoxide going this way off this ring. In humans, we get both alpha and beta, so that means the inoxide would be over here versus down there. We have two different systems here. So we have this amine addition before, so we have this kind of radical mechanism where we're forming the radical cation, and we have an anion, and then we're eventually forming an ylid there. The flavin monooxygenase is a little more complex, and so generally you only do secondary and tertiary aromatic amines, because flavin monooxygenase is always just a little more complex. There's a number of different pathways for N-demethylation, either going through an sp3 like structure or an aminium type structure. And in this case, they're able to actually isolate that R with the OH. So this is the carbonyl amine. So this is again one of the ways that they got proof that they had that form, that OH group alpha to the amine, that carbonyl amine. So carbonyl amine is forming because that anionic intermediate is able to abstract the proton here. So it's able to pull that proton off, and that's how we're getting, we're going from this radical ylid structure to a formal CH2 radical, and that's going to cause the bond scission that we get our carbonyl amine. Okay. And I will stop there.